Hi guys, in this video let's look into how do we design a nodal zones for Strut and tie model. In this case here we've got 2 meters by 6 meters long and 400 width of the concrete beam. And to do this we need to figure out a few things in terms of designing the ties and the prison struts and the bottom struts and what are the nodes conditions we need to design for. So let's have a look at the detailed calculation here. I've sort of laid out the calculation steps from step 1 to step 6. So basically, step 1 from designing the step 1 is to assume we have a lever arm that is JD assumed to be 85% of the depth of the beam. So that is giving us is 1.7 meters of the lever arm. And then we need to find out what is the angle here using trigonometry is at 41 degrees. So let's have a look at it here. So this angle here, theta is 41 degrees, and the JD assumed to be 85% of the depth. So so then we can work out what is the next thing is we're gonna work out the two things basically from step 2 to step 3. Step 2 is work out what are the member forces, right? The design forces are for the members, which is the bottle struts, the prison strut, and the tie. And also once we've got the member forces, and we need to look at what are the uh, dependable stresses on the nodes, right? So the members and the nodes, which in other words is the connections between. So we've got a connection between the bottle struts and the prison struts. In between them, it's got a links with which is this little triangle here. So we need to find out what are the allowable stresses for these little triangles. So we can in that essence, so we can design the reinforcement, right? So we work out step 2, we work out the bottle strut and ties. So based on the trigonometry, use the sine of the angle, and then follow that through. We can get the bottle struts and the ties and the prisons, because ties prisons are the same thing. Tension compression is the balance, and then we work out the using the formulas here, looking at the stresses of the and first of all looking at stresses of the bottle struts and the prison struts because of the compression ones, and then let's look at the stresses of the compressed CCC node, the connections, and the CCT node, the connections. At the bottom here, CCT node is here, CCC node is here because you have compression, compression, compression. You've got a compression and tension. So what are the allowable stresses or dependable stresses for those connections or nodes? All right. And next thing is, once we got that, the next is we're gonna looking at the geometry of the nodes. Okay, first of all, we're gonna looking at the CCC node first because CCC node is straightforward and we don't need to consider the reinforcement at the moment, so we can easily work out what is the required width for this prison strut. Because if you're looking at here, so this little width here, so the force is pushing outwards, trying to kicking out. So this face is subject to a compression. So we've already know the length of that face, which is the depth of the width of the beam, which is a 400, right? Which is the 400, and then so this thing over here, So you got compressions pushing through the face. So what is the required width here? So okay, so to do that, we're just using simply the force over the stress times length gives the area. That is the rewrite of the equation, which is the stress is the force over the area. So you substitute, you take out the width, and then you got the you take out the width. Eventually, you get to solved as 230 the width of the prison strut. So this vertical little length here is 230. And then we just need to make sure that what we assume is okay, because by looking at our the centroid of the prison strut is 115, and what we assume is 150. So yeah, it's within the right ballpark, so that's okay. And then next, we're going to look at the CCT node, because this node is a bit of a calculation intensive. So first of all, what I do is I figured let's draw the triangle, little triangle first. And we got the triangle here, triangle here. We need to work out what is the width of the tie because the tension trying to pulling. So what's the tension force? What's the phase required for the tension, right? And then we have a reaction here that is bearing. So what is required? The length for the bearing, right? The bearing plate. And then finally, we have this bottle strut strutting down onto my face. So what is the required? Is the face is enough? Because the face is going to determine by your tie and your plate. This forms a triangle of the hypotenuse area. So is that going to be okay to resist my bottle strutting? So these are the things need to be checked by CCT node. So same thing, we're going to use the simple formula here. We're going to force over the stress times the length, 400 width. That gives my 288. I'm going to say 300 of the width of the tie here. That's okay. And then let's work out, and then we can work out the centroid of the tie is 150 versus our assumed 150, which is fine. 150, okay. And then we can work out the required area of a reinforcement, which is the tie force divided by the stresses of the reinforcing bar. We're using 500 MPa, and then gives our required area of the reinforcing is this number, and it gives I'm using 32 bars diameter of bars, and it gives eventually ended up having 8 HD 32 bars. But let's look at how do we place the bar later on. And then we work out what's the required width of the plate for bearing, because this is anti-crushing stuff. So we're going to have my bearing reaction force that is 2000 kilonewtons onto my stress times my width. So that gives my minimum required width plate is 245, but I'm going to say I'm going to adopt 400 because you would have found that this is probably not governing the plate. It's going to be, you're going to have a lot more width because of the bottle strutting down here, causing a little bit of stresses. You need a more inclined angle here. So you try to get more bearing plate as much as possible, but not too much. But anyway, let's have a look at it. So by trigonometry, we can work out this hypotenuse area here. So the only thing is the bottle strutting is going to be perpendicular, strutting down to the node. So I've got a dashed line here just indicating the axis that is perpendicular. That's my bottle strutting face of it. And we need to work out what is that distance here and what is that distance here. I'm calling 1 and 2. So 1 plus 2 using a bit of a trigonometry, and it gives the actual vertical area 1 plus 2, that is 488. So my stress is, I can work out my stresses as a force over area, that is going to be 15.8, and you're comparing that to your CCT node at allowable stresses. CCT node, what's that? 20.4. So 20.4, which is well within that margin, which is okay. And then we're going to develop that once we got that geometry right. Sorry. And then we need to work out. Next step is to place the bars, right? And then we need to work out how do we place the bars in here. So first of all, we're going to buy 3101. We need a certain length of the bars to be developed, which is LDH. You can look at the clauses for that. There's an empirical equations here. You just substitute your values here using 500 megapascal times 32, and it gives us 425 millimeters required. See, that is required. So lucky I've got 400 bearing plate here, so I'm assuming that this is 400. And then through the centroid of my compression zone, the depth of compression zone is 300. Half of that is 150. So I've got utilize a little bit of this triangle area here. I'm gonna say a bit of laser here. I'm gonna say 45 degrees and 45 degrees. I got 150 on this side, and then my adjacent side would be, I'm just gonna say just 150. So adding those up, it's gonna have around more than 500. So I'm gonna say this is well more than what's required, 425, which is okay. So I say we have fully developed our tension bar. And then next we're gonna place the bars in here. So looking at here, we have basically if we need to develop the bars in the tension zone, in this compression zone anchored to be anchored in, we could do this. We could do a bend bar, just bend upwards. We can do that, but just work out what's the required clearance over here, and also what's the length over here, bend length. You can just look at the code according to the bar diameter. Or option 2 is going to have a welded plate over here on the side, and this plate will be pre-drilled holes, so you're protruding your bar through, okay, and then you cut it off and then weld it up. Then you can develop your tension bars. And the next option is, as I've shown here, just use a bar terminator. It costs a bit of more, but it's easy to do. Just cap it in, and you don't worry about the congestion issues here. So which is okay. And then the next step, we're going to check the CCC node. Same thing, we're going to check what's the actual perpendicular phase to it. And because strutting is coming perpendicular to the node, and we need to work out what is the stresses onto my face, and we can work out the phase 1 plus phase 2, that equals to minimum 435 mils, and we can work out what's the stress onto my compression strut, bottle strut here. This force over area gives me 17.7 megapascal. That is comparing to my CCC node allowable stress, which is 25.5. That's well within the margin. That is safe as well. Okay, and then for the bottle struts, we need, which is the horizontal and vertical reinforcements. So we need to check about the code. We still need to provide minimum reinforcement horizontally and vertically. So this is the equations we can looking on the code, and it gives my vertical minimum and my horizontal minimum. And then I'm going to use HT12 with 2 legs, because I'm going to I'm going to do something like that. So 2 legs, 2 legs, and my bars confined in here. So I have 2 legs, so I've got my area is 2 to 6. That's more than what's required, 200. Yeah, that's okay. And then check my spacing. This maximum is over 5 and 300. Pick one that is 300 governing, but I'm using 200 cc, so still okay. And then because I'm using 200 cc, I'm going to check my bar stresses provided and whether they are larger than 1.5 megapascal required. So I have my area of bar times my stress of a bar times my this because the strutting is to an angle, right? My bottle stress is angle, but I can't place my bars in an angle. It's difficult to do. The easiest way I'm going to place it horizontally and vertically, but the portion of my vertical bar tilting to an angle is they have a proportion of the strands working onto x-axis, right? And there's a portion of that working on the y-axis as well, so it's not fully working to both directions, but you have to rely on horizontal bars and vertical bars working together. That's why it's got a plus. Your horizontal bars and your vertical bars, and your sine, the angle of that means a proportion of that. If this is 45 degrees, you use about 70% of the vertical bars strength to work on the horizontal direction, and 70% of the vertical bars working on the vertical direction. And then your summation of those, and eventually you got your provided over the length of your spacing. That length of the spacing, that's how many number of bars I provided in my bottle strutting zone. That gives 2.1 megapascal. There's more than 1.5 megapascal required. That is okay as well. So this is the end of the strutting tie nodal zone designs. So to do it logically, first of all, you're going to work out what is the lever arms, and followed by what's the forces in my member, and what's the forces, what are forces in my connections, which is nodal zones. And followed by that, I need to check my nodal zones, my compression nodal zone, and my tension nodal zones. The tension nodal zone requires a bit of more calculation and more thoughts of in terms of placing your reinforcement. And then finally, you can check your CCC node, which is your bottle strutting. Check how many reinforcements you need in terms of horizontal and vertical. Make sure the overall stresses are provided as more than what's required 1.5. Then yeah, that's it. Thanks for watching.